Electrochemistry is really about turning redox chemistry into usable energy. In this part, the focus is on Daniell cells and the standard hydrogen electrode, because these two ideas give you the base framework for everything that follows. One thing to keep in mind from the beginning: a salt bridge is not a decorative part of the setup. It keeps the cell electrically neutral, and that is what allows the system to keep running. There are two broad kinds of electrochemical cells. A galvanic cell converts chemical energy into electrical energy, and it does so through a spontaneous reaction. Batteries and fuel cells are the classic examples. An electrolytic cell does the opposite. It uses electrical energy to force a non-spontaneous chemical change. That is why sodium hydroxide production and chlorine production are listed here. This distinction is fundamental because the whole chapter depends on separating spontaneous from forced processes. The Daniell cell is the cleanest example of redox turned into power. Zinc gets oxidized at the anode, Zn goes to Zn2+ and releases 2 electrons. Copper ions get reduced at the cathode. Cu2+ gains those 2 electrons and becomes copper metal. The overall reaction is Zn plus Cu2+ giving Zn2+ plus Cu. Under standard conditions, the cell potential is about 1.1 volts. If you understand this one cell properly, the rest of electrochemistry becomes much easier to visualize. The golden rule for galvanic cells is one of those things you should never confuse again. Left side, oxidation, anode, negative. That means oxidation happens at the left electrode, and that electrode is the anode. In a galvanic cell, the anode is negative relative to the solution. This is a high-yield memory trick because many students know the reactions but still mix up the labels. Electron flow and current flow are not the same thing, and that difference matters a lot. Electrons move from the negative anode to the positive cathode. Conventional current is defined in the opposite direction, from positive cathode to negative anode. Here's a trap you need to be aware of. Current and electrons do not travel together. The direction of current is always opposite to the electron flow. That convention is not optional. It is fixed by physics. The next idea is what happens when you add an external voltage smaller than the cell voltage. If the external potential is less than the Daniell cell potential, the cell keeps functioning normally. Zinc still dissolves at the anode, copper still deposits at the cathode, and electrons keep flowing from zinc to copper. In other words, business continues as usual. The external opposition is there, but it is not strong enough to stop the spontaneous cell reaction. When the external voltage exactly matches the cell voltage, the system shuts down completely. No electron flow, no current, no chemical reaction. This is an important conceptual point because it shows that the cell works only when there is a net driving force. At exact balance, the push and the opposition cancel each other out. That is the equilibrium point for the working cell. If the external voltage becomes larger than the cell voltage, the cell no longer behaves as a galvanic cell. It turns electrolytic. The external source forces electrons backward, so the natural direction is overridden. Zinc gets deposited at the zinc electrode, and copper dissolves at the copper electrode. Now this is where the examiner traps you. The same setup can switch identity depending on the external voltage applied to it. This comparison table is the clean summary of the two cell types. A galvanic cell converts chemical energy to electrical energy and works through a spontaneous reaction. An electrolytic cell converts electrical energy to chemical energy and needs a non-spontaneous reaction to be forced by an external source. The sign of the anode also differs. It is negative in a galvanic cell and positive in an electrolytic cell. One thing never changes though. Oxidation always happens at the anode. The expression for cell potential is written as E cell equals E right minus E left. That is why the diagram keeps changing minus E left. That is why the diagram keeps the anode on the left and the cathode on the right. The cell EMF is really the difference between the reduction potentials of the two half cells. The notation also matters. A single line shows a phase boundary, while a double line shows the salt bridge between the two electrolytes. The cell representation is not just syntax. It tells you the architecture of the electrochemical setup. Now we deal with a very important conceptual problem. Voltage is relative. You can know the difference between zinc and copper, but you cannot directly measure the absolute potential of a single half cell in isolation. That is why electrochemistry needs a zero reference point. The analogy with sea level is perfect here. Just as heights are measured relative to sea level, electrode potentials are measured relative to a standard reference. That reference is the standard hydrogen electrode, or SHE. It is assigned a potential of exactly 0.00 volts under standard conditions. The setup uses platinum, hydrogen gas, and hydrogen ions in solution. With the notation, the reaction is H plus plus an electron, giving half a molecule of hydrogen gas. This electrode is the benchmark for all other electrode potentials, so it sits at the center of electrochemical measurement. For SHE to remain a true zero reference, the conditions have to be exact. Hydrogen gas pressure must be 1 bar, the concentration of hydrogen ions must be 1 molar, and the platinum electrode must be coated with platinum black to provide a highly active surface for rapid equilibrium. Here's the main point. She is only 0.00 volts when the standard conditions are strictly maintained. If any one of them changes, the reference is no longer exact. Electrochemistry becomes easy once you see the full system, not just the formulas. In this part, the focus is on galvanic cells, electrode potentials, and the Nernst equation. That means we are moving from the basic cell setup to the ranking of metals, then to non-standard conditions, and finally to how cell potential changes in real situations. This is the point where electrochemistry starts behaving like a complete toolkit instead of a set of isolated equations. Start with the galvanic cell itself. The left side is the anode, where oxidation happens, so electrons are lost there and the electrode is negative. The right side is the cathode, where reduction happens, so electrons are gained there and the electrode is positive. The easy memory rule is the lone rule. Left equals oxidation equals anode equals negative. And the key formula is simple. E cell equals E right minus E left. Cell notation is just a compact way of writing the flow of a redox cell. In the example, Cu solid plus 2Ag plus aqueous yields Cu2 plus aqueous plus 2Ag solid. Copper is the anode half cell and silver is the cathode half cell. A single vertical line marks a phase boundary, and the double line represents the salt bridge connecting the two electrolytes. The key idea is that notation tells you where oxidation and reduction happen without writing the whole story every time. The standard hydrogen electrode, or SHE, is the reference point for all electrode potentials. It uses a platinum wire coated with platinum black, pure hydrogen gas at exactly 1 bar, and acidic solution with a concentration of H plus equal to 1 molar. By convention, the potential of SHE is assigned 0.00 volts at all temperatures. The standard half-cell reaction is H plus aqueous plus E minus yields 1/2 H2 gas. This is the baseline from which every other electrode potential is measured. Once the SHE baseline is fixed, metals can be compared. In the example on the page, copper has E0 equals positive 0.34 volts, while zinc has E0 equals negative 0.76 volts. A positive standard reduction potential means the species is reduced more easily than H+. A negative value means it is more willing to oxidize and donate electrons. Here's a trap you need to be aware of. Copper's positive E naught is exactly why it does not dissolve in HCl, while zinc does. The electrochemical series is the ranking list of reduction potentials. At the top sits F2 plus 2E minus yields 2F minus with E naught equals positive 2.87 volts, showing the highest tendency to get reduced. The middle baseline is 2H plus 2E minus yields H2 with E naught equals 0.00 volts. At the lower end is Li plus E minus yields Li solid with E naught equals negative 3.05 volts, showing the maximum tendency to get oxidized. So the series is really a ladder of oxidizing strength and reducing strength. That ladder separates oxidizing agents from reducing agents very cleanly. The strongest oxidizing agent has a highly positive E naught and wants electrons aggressively, with fluorine as the champion. The strongest reducing agent has a highly negative E naught and donates electrons aggressively, with lithium metal as the champion. The quick conceptual test on the page makes the point nicely. Zinc is a stronger reducing agent than copper, so a zinc pot would dissolve in a CuSO4 solution, while copper would not in acid. The Nernst equation shows what happens when conditions are not standard. The general form on the page is E equals E naught minus the quantity RT over NF naught minus the quantity RT over NF times the natural log of 1 over the concentration of Mn plus, which tells you how cell potential changes with concentration. The terms matter. R is the gas constant, T is temperature in Kelvin, N is the number of electrons transferred, and F is Faraday's constant. Here's a trap you need to be aware of. The concentration of a solid is taken as unity, so only the aqueous species appear in the expression. For the Daniell cell, the Nernst equation is written separately for copper and zinc half cells and then merged into the final cell expression. The final master result is E cell equals E naught cell minus the quantity RT over 2F times the natural log of the concentration of Zn2 plus divided by the concentration of Cu2 plus. The exam takeaway is direct. E cell increases when the concentration of Cu2 plus goes up, and E cell decreases when the concentration of Zn2 plus goes up. That is the practical way to read concentration effects in a galvanic cell. The log form is the same Nernst equation written in a friendlier way for numerical work. At 298 Kelvin, it becomes E cell equals E naught cell minus the quantity 0.059 over N times the log of the concentration at the anode divided by the concentration at the cathode. The page also gives a classic shortcut. If the problem is at 25 degrees Celsius or 298 Kelvin, you can skip the natural log form and use the base 10 version directly. That saves time and reduces algebra mistakes in exams. The universal Nernst equation works for any redox reaction of the form AA plus BB gives CC plus DD. The general form is E cell equals E standard cell minus RT upon NF natural log Q, where Q is the reaction quotient. The quotient is written as Q equals concentration of C raised to power C multiplied by concentration of D raised to power D divided by concentration of A raised to power A multiplied by concentration of B raised to power B. Here is the critical rule. First, balance the equation completely. Then, make sure the same number of electrons, called N, is transferred in both half reactions before applying the Nernst equation. That is the step where many problems go wrong. The universal Nernst equation works for any redox reaction of the form AA plus BB gives CC plus DD. The general form is E cell equals E standard. Now let's learn about three connected ideas: Nernst equation, Gibbs energy, and conductance. The slide is setting the frame for the whole unit. One part tells you how cell potential changes with concentration. Another tells you how that potential links to thermodynamics. And then we move into how current actually flows through solutions. The triangle on this page is the heart of the chapter. If you know any one of these three quantities, E naught cell, delta R G naught, or Kc, you can calculate the other two. The three relations are delta R G naught equals negative N F E naught cell. E naught cell equals the quantity 2.303 RT over NF times the log of Kc. Delta Rg naught equals negative RT times the natural log of Kc. That is the concept check. These are not isolated formulas. They are one thermodynamic system seen from three angles. This slide focuses on equilibrium in an electrochemical cell. When the system reaches equilibrium, E cell becomes zero because the reaction stops and the driving force disappears. The derivation shows the Nernst equation being reduced at equilibrium, leading to the shortcut at 298 Kelvin. E naught cell equals the quantity 0.059 over N times the log of Kc. The warning box is important. If a battery is dead, its actual E cell is zero, but that does not mean the standard cell potential is zero. The standard value remains fixed. The next link is between Gibbs free energy and cell potential. The master relation is delta Rg equals negative NFE cell. The slide separates the two properties clearly. E cell is intensive, so it does not change if the reaction is multiplied. Delta Rg is extensive, so it depends directly on N, the number of electrons transferred. The example proves the point. Doubling the reaction doubles delta Rg, but E cell stays the same. This page gives the basic relations of resistance, conductance, resistivity, and conductivity. Resistance: R equals ρ times the quantity L over A. Conductance: G equals 1 over R, which equals kappa times the quantity A over L. Resistivity: ρ equals R times the quantity A over L. Conductivity: kappa equals 1 over ρ, which equals G times the quantity L over A. These are the formulas that let you move between the geometry of a sample and its ability to carry current. The units are just as important as the formulas. Measuring conductance in an ionic solution is not as simple as plugging a wire into a circuit. Two problems are shown here. First, direct current changes the composition of the solution because electrolysis occurs. Second, a liquid solution cannot be connected directly to a Wheatstone bridge like a solid wire. The two solutions are: use alternating current instead of DC. Use a specially designed conductivity cell. That is the practical setup used in conductance measurements. The conductivity cell hardware is the next step. The cell uses platinized platinum electrodes, and the solution between them behaves like a conductor with a measurable length L and cross-sectional area A. The important idea here is the cell constant, written as G star. It bridges the physical geometry of the cell and the electrical behavior of the solution. G star equals L over A, which equals R times kappa. The page also gives the useful laboratory trick. Determine the cell constant first using a standard KCl solution of known conductivity. After that, the same cell constant can be used for further measurements. The Wheatstone bridge method is used to determine unknown resistance. First, the bridge is balanced so no current passes through the detector. Then, the unknown resistance is calculated using the ratio relation. Finally, conductivity is obtained from the cell constant. The logic is simple. Measure resistance first, then convert it into conductivity. The bridge is the instrument, the cell gives the chemistry. This page introduces molar conductivity, written as lambda Em. Conductivity changes because concentration changes, so it is not always the best comparison measure. Molar conductivity solves that problem by defining the conducting power of exactly 1 mole of electrolyte, regardless of how much solution is present. The formula is lambda Em equals kappa divided by C. So conductivity is about the solution as it is, while molar conductivity standardizes it to 1 mole. Unit conversion becomes important here. The units of kappa and concentration C must match properly. The slide shows two paths. If kappa is in Siemens per centimeter, then lambda Em equals kappa times 1000 divided by m. If kappa is in Siemens per meter, then lambda Em equals kappa divided by the quantity 1000 times m. The final units become CGS path, Siemens centimeter squared per mole, SI path, Siemens meter squared per mole. And the conversion given is useful to keep in mind. 1 Siemens meter squared per mole equals 10 to the power of 4 Siemens centimeter squared per mole. Dilution changes the two conductance measures in opposite ways. As dilution increases, conductivity kappa decreases because ion density per unit volume drops. Molar conductivity, lambda Em, increases because 1 mole of electrolyte has more total volume in which ions can move more freely. So kappa tracks the density of ions, while lambda Em tracks the freedom of ions in solution. That distinction is a very common concept check. So the focus shifts from basic electrochemistry formulas to how ions actually behave in solution. The opening frame already tells you the direction. First, conductivity relations, then dilution, then graph behavior, then weak electrolytes, and finally, Kohl-Rausch's law as the main tool for limiting molar conductivity. Start with the basic conductivity chain. Resistance leads to resistivity, resistivity leads to conductivity, and conductivity leads to molar conductivity. The slide writes it as a sequence of relations. R leads to rho, which equals R times A over L. Rho leads to kappa, which equals 1 over rho. And kappa leads to lambda Em, which equals kappa times 1000 divided by C. The important trap is the unit system. If the question demands Siemens meter squared per mole, the formula changes accordingly. In exam work, the safest habit is to stick with cubic centimeters per centimeter units unless the question forces SI conversion. Dilution changes the two conductivity measures in opposite ways. As water is added, conductivity decreases because the number of ions per unit volume drops. At the same time, molar conductivity increases because the total volume containing 1 mole of electrolyte becomes larger and ion movement becomes easier. That is the core idea behind the seesaw diagram on the slide. Kappa tracks ion density. Lambda Em tracks freedom per mole. The graph of molar conductivity against the square root of concentration is one of the most important visual ideas in conductance. For strong electrolytes, the line is almost straight and can be extrapolated to the y-intercept to get limiting molar conductivity, lambda m naught. For weak electrolytes, the curve bends sharply and does not touch the axis cleanly, so direct extrapolation fails. That difference is the whole reason Kohl-Rausch's law becomes necessary. Strong electrolytes follow a linear relation of the form lambda m equals lambda m minus a times the square root of c. This behaves like a straight line equation, intercept plus slope term. The constant a depends on the charge type of the electrolyte, and the slide highlights the key rule. Electrolytes with the same charge type share the same a value. So 1 to 1, 2 to 1, and 2 to 2 types follow the same broad pattern within their class. Weak electrolytes do not obey the straight line extrapolation method. At infinite dilution, their degree of dissociation increases in a way that breaks the direct graph method. That is the limitation shown here. So the question becomes, if the graph fails, how do we find lambda m naught for a weak electrolyte? The answer is Kohl-Rausch's law of independent migration of ions. Kohl-Rausch's law says that at infinite dilution, each ion contributes independently to the total limiting molar conductivity. The master formula is lambda m naught equals nu plus times lambda naught plus plus nu minus times lambda naught minus. That means total limiting molar conductivity is the sum of the individual ionic contributions multiplied by their stoichiometric numbers. The stoichiometry trap matters here. For CaCl2, the chloride contribution must be counted twice. This page shows how Kohlrausch's law is used for a weak electrolyte, specifically acetic acid. Since acetic acid is weak, we cannot directly measure its limiting molar conductivity from the graph. So we build it indirectly using strong electrolytes that contain the ions we want. The algebraic trick is simple. Add the conductivities of strong electrolytes that supply the required ions, then subtract the unwanted garbage ion contribution. That is the logic behind lambda m naught of HAC equals lambda m naught of HCl plus lambda m naught of NaAC minus lambda m naught of NaCl. Once both lambda m and lambda m naught are known, we can calculate the degree of dissociation, alpha. The formula is alpha equals lambda m divided by lambda m naught. After that, the dissociation constant follows from the concentration and alpha. K equals C times alpha squared divided by the quantity 1 minus alpha. So this page shows the complete workflow for weak electrolytes. First find current molar conductivity, then limiting molar conductivity, then degree of dissociation, and finally the dissociation constant. The numerical example walks through that exact process. Given concentration, conductivity, and limiting molar conductivity, the solution first calculates lambda m, then finds alpha, and finally computes K using the weak electrolyte formula. This is the kind of question where unit handling and formula order matter more than lengthy theory. Electrolysis is the process in which electrical energy is used to force a chemical reaction. The power source pushes electrons through the circuit. The anode is the positive electrode where oxidation happens, and the cathode is the negative electrode where reduction happens. Inside the electrolyte, cations move toward the cathode and anions move toward the anode. In the copper purification setup, impure copper acts as the anode and pure copper as the cathode. So copper dissolves from the impure side and deposits on the pure side while impurities are left behind. The central relation here is simple. Charge equals current multiplied by time, or Q equals I times T. 1 Faraday is the charge of exactly 1 mole of electrons. For exam work, the practical value is taken as about 96,487 coulombs per mole. And the slide also reminds you to use 96,500 coulombs as the quick MCQ value instead of wasting time on exact decimals. For the copper sulfate example, the current is 1.5 amps and the time is 10 minutes, which gives a total charge of 1.5 times 600 equals 900 coulombs. Since copper deposition follows Cu 2 plus 2E minus yields Cu, 63 grams of copper requires 2 Faradays of charge. Using the unitary method, the deposited mass comes out to 0.2938 grams. The real habit to build is this. First calculate charge, then relate charge to electrons, then convert that into mass. When more than one ion is present, they compete for the electrodes. At the cathode, reduction takes place and the species with the higher reduction tendency wins. At the anode, oxidation takes place and the species with the lower oxidation resistance wins. Inert electrodes like platinum and gold only provide a surface. They do not take part in the reaction. Reactive electrodes, on the other hand, can themselves enter the chemistry. This competition logic is what decides the actual product, not just the written ions in the solution. Let's move on to molten versus aqueous sodium chloride. Molten NaCl is the straightforward case. Sodium ions are reduced to sodium metal at the cathode, and chloride ions are oxidized to chlorine gas at the anode. Aqueous NaCl is trickier Because water also competes. At the cathode, Na plus competes with H plus and hydrogen wins. At the anode, Cl minus competes with water and chlorine wins because of oxygen overpotential. That is why the net result is NaOH aqueous plus Cl2 gas plus H2 gas. Here's the trap to be aware of. In aqueous solutions, the thermodynamically obvious answer is not always the product that actually appears. Effect of concentration in sulfuric acid. Concentration changes the product. In dilute sulfuric acid, water is oxidized and oxygen gas is produced. In concentrated sulfuric acid, the oxidation product changes to peroxodisulfate S2O8 2-. That shift is important because it shows that product formation depends not just on the electrolyte but on its concentration as well. A galvanic cell works in the reverse direction of electrolysis. Chemical energy is converted into electrical energy. Primary batteries are one-time use systems, so once the reaction runs out, they cannot be reused. The slide highlights two key exam targets, the dry cell and the mercury cell. Those are the two battery types you want to know cleanly for this chapter. The dry cell, also called the Leclanché cell, gives about 1.5 volts. The zinc container is the anode or outer shell. The carbon graphite rod with manganese dioxide is the cathode system in the center. The electrolyte is a moist paste of NH4Cl and ZnCl2. A key concept to remember is that manganese is reduced from +4 to +3 and ammonia gas is not simply released. It combines with Zn2+ to form the complex Zn, NH3 taken 4 times with a 2+ charge. The mercury cell is used in low current devices like watches and hearing aids because it provides a constant voltage. The anode is zinc amalgam ZnHg. The electrolyte is a KOH plus ZnO paste. The cathode is HgO with carbon paste. It is described as a flat battery and the overall reaction shown is ZnHg plus HgO yields ZnO solid plus Hg liquid. The key idea here is constant output for small devices. A secondary battery is rechargeable, meaning it can be restored by passing current in the opposite direction. That is the defining feature. The slide also gives the physics shift. When discharging, the cell behaves like a galvanic cell. When charging, it behaves like an electrolytic cell. That reversal is the whole idea behind rechargeability. The lead storage battery is shown in both discharging and charging modes. During discharge, both the anode and the cathode end up forming PbSO4 as a solid precipitate. The electrolyte is about 38% H2SO4 solution. During charging, the process reverses, regenerating sulfuric acid and restoring PbO2 on the cathode and Pb on the anode. That reversible chemistry is why the lead-acid battery can be reused. The nickel-cadmium cell is another secondary battery. It is shown in the familiar jelly roll form. The anode is cadmium, the cathode is nickel oxyhydroxide related, and the separator keeps the electrodes apart. The slide emphasizes the trade-off. This battery lasts longer than a lead storage cell, but it is more expensive to manufacture. The key discharge idea is that cadmium gets oxidized while nickel species change accordingly. Fuel cells are different from conventional batteries. They are galvanic cells that convert the energy of combustion fuels directly into electrical energy. That is the real advantage. Fewer steps, less loss, better efficiency. The slide compares the old thermal plant route with the fuel cell route and shows the efficiency jump clearly. around 40% versus 70%. Another crucial feature is continuous feed. As long as fuel is supplied, the cell keeps working. The H2O2 fuel cell is the classic example. Hydrogen and oxygen are fed in, and water is produced as the final product. The electrolyte is concentrated aqueous NaOH, and the electrodes are porous carbon with PT or PD catalysts. The overall reaction is simply the combination of hydrogen and oxygen into water. The slide also points out a famous application. This cell powered the Apollo space program, and the water produced could even be used directly for astronauts. Corrosion is the next major topic, and the slide defines it clearly. Rust is not random damage, but an unwanted parasitic electrochemical cell on the metal surface. Iron acts as the anode, oxygen from air acts as the cathode, and water provides the medium. The metal is literally powering its own destruction through an electrochemical pathway. That idea is the conceptual core of corrosion. The rust formation mechanism is shown step by step. Iron at the anode is oxidized to Fe2+. Oxygen at the cathode is reduced in the presence of water and H+ ions. The Fe2+ is then further oxidized to hydrated ferric oxide, which is the rust you actually see on the surface. The slide also gives the trap. The H+ ions are believed to come from carbonic acid, H2CO3, formed when atmospheric CO2 dissolves in water droplets. Corrosion prevention is divided into three methods. First, barrier protection, where the metal is physically blocked from air and moisture using paint or chemicals like bisphenol. Second, inert coating, where the iron is covered with another unreactive metal such as tin. Third, sacrificial electrode protection, where a more reactive metal like magnesium or zinc is attached so it corrodes instead of the iron. The key idea is that the sacrificial metal must have a lower standard reduction potential than iron.